So we're going to talk more about energy in a later lecture, but we're just going to very briefly touch on it now. So like I said, every reaction has an energy change that goes with it. Here, this is a combustion reaction of methane with oxygen. We're just burning methane. There's an energy change occurring here. How do you observe that energy change from that flame? Okay. When I say fire, what do you think?
Hot.
Hot. That's an energy change. Hot means heat. That heat is coming from somewhere. The heat is coming from the reaction. In this case, the heat is released from the reaction into the surroundings. If you're using that flame to cook, whether it's in the lab, you're going to have a Bunsen burner, or it's in your stove at home and you're using it to cook, whatever it is you're trying to heat is the surroundings. Okay? For us, the surroundings is everything except the reaction. So if you have a reaction happening in a beaker, the beaker itself is the surroundings. The thermometer that might be in the reaction is the surroundings. Your hand that's holding the beaker is the surroundings. Theoretically, the entire universe is the surroundings, except for the reaction itself. So we're going to be talking about energy that comes from everything other than the reaction going into the reaction, or leaving the reaction going into everything else. Every change, whether it be a chemical change or a physical change, has an energy change that goes with it. Think about if I just take a pencil and I break that pencil, I just take it and snap it in half. Is that a chemical or physical change? Physical. Where does the energy change come in? Where is the energy involved in that? I had to put energy into it to break it. There are energy changes in every physical or chemical change that happens. So we have two types of reactions. Some reactions absorb heat, some reactions give off heat. The ones that give off heat are a lot more common, but the ones that absorb it aren't exactly uncommon. So this is an exothermic reaction. Exothermic reaction gives off heat. An endothermic reaction absorbs heat. What we have here are what we call energy diagrams for a reaction. We have, this is just a graph. On the x-axis, we have time. So this is from the beginning of the reaction to the end of the reaction. So we're just going forward in time as we go left to right. On the y-axis is energy. The higher you are up on the y-axis, the more energy you have. So in an exothermic reaction where we are giving off heat, we start here, we draw a line for the reactants, and then we lose energy, and then we finish down here at the products. In an endothermic reaction, we gain heat in the reaction, and so we start low with the reactants and end high with the products. What you're looking for is which is higher, the reactants or the products. If the reactants are higher, we must have lost energy. So that's an exothermic reaction. For an endothermic reaction, we are gaining heat, and so the products are higher. That's pretty straightforward. Where people get confused is what happens to the temperature of the surroundings. Remember that if you are touching a reaction, your hand is the surroundings, not the reaction. So if you think about it, if I touch an exothermic reaction, is it going to feel hot or is it going to feel cold? Exothermic reaction is losing heat. That's what everyone always says. It's hot. Why? Do you know why it's hot? It's pushing out heat. Where's it pushing out heat into? Your hand. the surroundings. So, in an exothermic reaction, the reaction itself is losing energy, but the energy has to go somewhere. It leaves the reaction and goes into your hand. And so your hand feels hot. In an endothermic reaction, the reaction is gaining energy. Is it going to feel hot or cold? Cold. Yes, it's the opposite, so you could guess that. But can you explain to me why your hand feels cold? Yeah, Kevin.
Take energy away from your hand.
Perfect, yes. The reaction is taking in energy. It has to get that energy from somewhere. Your hand is touching the reaction, so it's going to suck the energy out of your hand into the reaction. If your hand loses energy, it gets cold. So, you have to remember, exothermic reaction feels hot, endothermic feels cold. If you can't or don't want to remember the reasoning, my suggestion is remember the best example of an exothermic reaction is fire. And you know that fire feels hot. And so, an exothermic reaction must feel hot. So, if you remember, hydrogen is very flammable. So if you fill a balloon with hydrogen gas and give it a spark, it'll blow up. There's fire there. That's hot. That's an exothermic reaction. Most chemical reactions are exothermic. But some are endothermic. Can you think of an example of an exothermic reaction other than fire? Can you think of what is something where you mix two things and it gets hot?
The hand warmer things?
Hand warmer things, yes. What's in there? There's two chemicals. One of them is inside of a little packet. When you squeeze it to activate it, you bust open that packet, you mix the two chemicals, they react. It's an exothermic reaction, and it gets hot. Can you think of an example where you mix two things and it gets cold? Yeah, Kevin.
Simple compressed uranium water.
Say it again.
Uranium water and simple compressed.
Say uranium water?
Uranium and simple.
Oh, okay, yeah.
What about an icy hot pack? What is that?
I'll get to that. So what Kevin's talking about is what's in the instant cold packs. So Jonathan had the instant hot packs for an exothermic reaction. For an endothermic reaction, there are two chemicals in there that when you mix them, they react. They absorb heat. So if you put it on your swollen ankle, it's going to suck the energy out of your ankle and make your ankle cold. With the icy hot, to be honest, I don't know whether the icy hot actually, I've never used icy hot. I don't know if it actually gets hot and then cold, or if it just makes your body feel hot and cold. Like if you eat something spicy, your mouth feels hot, right? That's capsaicin in there. It doesn't actually make your mouth hot. It binds to the heat receptors and makes them think it is hot. Cold, menthol, like cough drops, it feels very cold. Cough drops don't actually make your mouth cold, it just makes your mouth feel cold. So I don't know if icy hot actually gets hot and cold, or it just makes you feel hot and cold.
What about dry ice?
Dry ice, that is, you're making the dry ice, if you put it on your hand, very cold, right?
Mm-hmm.
So what did we learn about what happens to dry ice when it gets heated? It goes from a solid to what? A gas. It sublimates. Just like you have to put energy in the water to make it boil, you have to put energy into the carbon dioxide, the dry ice, to make it sublimate. And so that energy has to come from somewhere.
So it's pulling.
It's pulling the energy out of your hand. Yeah. You have to be careful about talking about whether something, an object, is not endothermic or exothermic. A process or a change is endothermic or exothermic. So dry ice itself is not endothermic, the process of it sublimating is endothermic. So if you put your hand into ice water and you make that ice melt, the melting is endothermic, but the ice itself is neither. Okay, so that's the end of energy changes. We're going to come back and talk a lot more about those then, but that was just kind of a good little place to throw an introduction into that, because we just talked about all those reactions. So this is our last type of a reaction. So we had the four main ones plus combustion, and then I said there's another one, there's a last one. This, you can kind of think of it as its own type of reaction, but in reality, it's a subtype of the other ones. Some of the synthesis reactions, some of the decomposition, some of the single, some of the double displacement fit the category of oxidation reduction reactions. An oxidation reduction reaction is a reaction that transfers electrons. If you look at the atoms and how they get rearranged, electrons are being transferred. Reactions happen because of electrons. The atoms themselves just sort of follow the electrons around. We call oxidation reduction reactions redox reactions. So in this example, we have zinc. We're mixing it with a copper solution. And when we do that, we get zinc ion and copper metal. So we started with zinc metal and copper ion and got the zinc ion and copper metal. What happened in this reaction was that electrons were transferred from the zinc to the copper. And that was the reaction that happened. So this is a picture of that going on. This is a chunk of zinc, and it's in a solution of, let's say, copper nitrate. When you dissolve copper nitrate, the copper ion is blue. And so we have this solution here. And so, at a molecular level, what we have is this is the zinc, and then floating around out here are the red copper ions. And if one of those copper ions comes in contact with the zinc, an electron from the zinc is going to get transferred over to the copper ion. Now if we look at our reaction here, what does that charge on that copper mean in terms of the electrons that it has? Why does it have a 2+ charge? Say it again. Yeah, I think you were right. It's missing 2 electrons, yes. Copper lost 2 electrons to get the 2+ charge. So if we go from copper 2+ to copper neutral, what had to have happened with the electrons? The reverse. It gained 2. Zinc went from neutral to +2. So what happened to its electrons? It lost 2. So each of these zincs gives 2 electrons to one of these coppers. And so this goes from neutral to +2. That goes from +2 to neutral. So these are called oxidation reduction reactions because in a reaction, there is both oxidation and reduction happening at the same time. Oxidation is the process of losing electrons. So if we go back, zinc lost electrons. It underwent oxidation. We say it is oxidized. The opposite is reduction. Reduction is gaining electrons. If we go back and look at this reaction again, the copper gained electrons. To me, the easiest way to remember which is reduction has the root word reduce. If you gain electrons, your charge gets reduced. In this case, we went from +2 to 0. That number went down. That charge went down, the charge got reduced, and so copper got reduced, and then by default, process of elimination, zinc must have been oxidized. You can also be reduced. Let's say you go from 0 to -1. 0, -1 is down. -1 to -2 is still down. That number is being reduced, and so the atom is being reduced. Other people have learned, I don't use this, but the acronym Leo the Lion says GER. Lose electrons oxidized, gain electrons reduced. If you want to use that, go ahead. That's not something I use myself. So oxidation and reduction always happen as a pair. Electrons don't magically just fly off into space. If something is losing them, something is gaining them also. And if something is gaining electrons, they certainly came from somewhere. So oxidation and reduction always happen together. Remember that the element whose charge goes down is the one that is reduced. And where it gets tricky is we have a couple other definitions we have to take care of as well. The thing that gets reduced is called the oxidizing agent because it oxidizes the other thing. And so the thing who gets oxidized is the reducing agent. You have to know both terms. You have to be able to figure out which thing got reduced, which thing got oxidized, which is the reducing agent, which thing is the oxidizing agent. And you have to remember, the thing that gets oxidized is the reducing agent. It's switched. The thing that gets oxidized is not the oxidizing agent. The thing that gets oxidized is the reducing agent. The thing that gets reduced is the oxidizing agent. So let's look at another example. This is essentially what was going on in that reaction, but it's the whole thing. So rather than just showing copper ions, we have the whole solution. It was copper chloride. So in order to figure out what got oxidized and what got reduced, we have to assign what we call oxidation numbers. Okay? For the most part, it's just going to be the charges. So in this case, the oxidation numbers are already written for you. So we're not going to learn how to write them just yet. We're going to look at this example where they're already written for us. So this zinc has an oxidation number of 0. Then we have 2 plus, 1 minus, 2 plus, 1 minus, and 0. So you look at that, and you say, which element has an oxidation number that went down? Which element has an oxidation number that went down from the left to the right? Copper. It went from +2 to 0. So copper was reduced. Zinc went up. It went from 0 to +2. It went up. That's oxidation. Chlorine didn't change. Chlorine is a spectator ion. It does nothing here. So it has no specific name. So we have a list of rules for assigning oxidation numbers. These rules can get hairy, but the hairy ones are 3 and 4. I've erased them. You don't need to worry about them. The only ones you need to worry about are the easy ones. Okay? It says number 1 says the oxidation number of atoms of an uncombined element is 0. What that means is an element by itself. So here, zinc is just by itself. So the oxidation number is 0. Over here, copper is by itself. And so it is 0. If an element is by itself, it's 0. That's rule number 1. Number 2 says the oxidation numbers for a molecule have to equal 0. So we go back and look at copper chloride. This copper is positive 2, and that each chlorine is negative 1. But there's 2 of these negative 1s, and so you have positive 2, negative 2, it's 0. That's rule number 2. Each molecule has to come out to be a total of 0. And number 5 just tells you if you're dealing with an element that's in a compound, just look at the periodic table and say, if I was making this an ion, and I was going to give it a charge, what charge would I give it? And that's the oxidation number. So sodium, right here, what charge would you give a sodium ion? +1. So the oxidation number of sodium is +1. Calcium is +2, and so it has an oxidation number of +2. Fluorine, chlorine, bromine, they all form -1 ions, and so they are going to have oxidation numbers of -1. So assigning oxidation numbers isn't hard. If an element by itself, give it a 0. If it's in a compound, look up here and give it an oxidation number just like you would give it a charge. You already know those charges, you just get to reuse them again. So, what is the oxidation number of magnesium here? 0. It's an element by itself, and so the oxidation number is 0. Let's jump down, we'll skip number 2, we'll go to 3, we'll come back to 2. In sodium chloride, what's the oxidation number on the sodium? +1. What's the oxidation number on the chlorine? -1. You can get that 2 different ways. The easy way is saying chlorine forms a -1 charge, so it must have an oxidation number of -1. You also could have used rule 2 and said sodium is +1, the whole thing has to equal 0, so chlorine must be -1. Now we can come back to 2. The rules 3 and 4, the ones I cut out, deal with things like carbon. Okay? What you need to know about carbon is that carbon can do wacky things. So we're not going to try to automatically assign it anything. Chlorine forms a -1 charge. And so we have -4 here, total. So what does the oxidation number on the carbon have to be? +4. So, so we have Cl4. Each chlorine has a -1. Because chlorine forms a -1 charge. There are 4 of them. And so I would write the oxidation number for chlorine -1-, but there are 4 of them. And so we have a total of -4 here. And the thing as a whole has to equal 0, so this 1 carbon must be 4+. I think on quizzes and exams, you're going to have things more like that, where you don't have to do that process of elimination. You can look at that and say sodium forms a +1 charge, chlorine forms a -1 charge, so those must be the oxidation numbers. So we use oxidation reduction reactions quite often. You just don't realize it. Rust or corrosion is an oxidation reduction redox reaction. So this is an old car. New cars don't really rust. Old cars used to rust really bad, especially if you're up north with the salt on the road. So this is iron. This is a spot of rust. This is a water droplet. In the water droplet, there's obviously water, and then there's oxygen from the air that's in the water. So what happens is the oxygen in the air steals electrons from your iron. It comes on, the electrons go from the iron into the oxygen, but then the oxygen leaves with the iron's electrons. So the electron ends up turning to rust. Sorry, the iron turns to rust. If you have copper or brass, it's also an oxidation reduction reaction when it corrodes. If you have silver jewelry, when it corrodes, it's an oxidation reduction reaction. We can prevent that from happening though. If you're going to have corrosion, the oxygen is going to steal the electron from the thing that is the easiest to steal from. So, if you've ever seen a giant ship, the hull is usually made of steel. Steel rusts. But sometimes you see these little plates on them. They're usually below water, but there are some that are above sea level. These are zinc plates. Zinc gives off electrons a whole lot easier than steel. So the oxygen in the water will steal the electrons from the zinc rather than the hull. If the oxygen does steal an electron from the hull will just turn around and steal one from the zinc. And so the hull itself doesn't corrode because it keeps its number of electrons. Once these get bad, you take it off, you put a new one on. Anybody have an outboard motor? If you've ever noticed, just above the prop, right there, there's a little removable piece of zinc. It's about, depending on the size of your motor, it's about that big or smaller. There's one on each side. There's also usually some where it attaches to the transom here. There's usually also a little fin that comes down right here. It helps control the torque from the propeller so that the steering wheel doesn't just go crazy. But that's also made of zinc. That's these. They fit right under here. So your outboard motor has all these replaceable zinc parts on them. If you use it in fresh water, it's probably not going to corrode fast enough that you'll ever have to replace it. I've never owned a saltwater boat, so I don't know if you store it in salt water, how often you have to replace it. They do the same thing on oil pipelines. Can you imagine having an oil pipeline that rusts? Not only is it a disaster waiting to happen, but these things are thousands of miles long. You don't want to have to pay somebody to walk thousands of miles of oil pipeline in grizzly bear country looking for spots of rust. And so they put these pieces of zinc equally spaced throughout it, and occasionally they go through and replace that zinc. But that is very infrequent. They don't have to do that very often. You can also just paint something. For that reaction to happen, the steel has to touch the water. If there's paint between them, they can't react. These pieces of zinc are called sacrificial anodes. An anode in electricity is the pole that gives off electrons. So this is giving off electrons, and it's sacrificial because you want it to degrade. It's going to degrade so that your expensive thing doesn't degrade. You can just replace it. Electroplating is the reverse reaction. Yes, it's a gold-plated DeLorean. Basically what you do is you put whatever you want to plate in a solution of gold ion, and you run electricity through it. You put electrons into the gold ion. So if gold is in ion form, and you give it 2 electrons, it goes to that. That is gold metal. It has to go somewhere. And so it sticks to whatever metal is in your solution. Okay. That's the end of our redox reaction. So what I showed you for redox reactions is not that complicated. You can be thankful about that because redox reactions could be 2 to 3 weeks on their own. They get really nasty, but luckily for you, you don't have to learn the nasty stuff. Questions about stuff we talked about there? Say it again? This lecture we just finished? Yeah. So we're going to move on to number 7.
Should review 6.
Say it again?
So we should review 6 too.
Yeah, we really should.
No,
no idea what I'm doing.
Well, when we do the homework, that'll include.
But the homework,
So
it like none of the notes explained the homework. It was like totally different.
We'll do that when we deal with that when we get there. So the goal for today is to also finish 7. If we don't, we don't. Okay? The test will reflect whatever we get through. The question?
Our next test is on the 11th, correct?
It's next Tuesday. Guess that's it. Yeah. And so next exam is next Tuesday. It is on lectures 5, 6, 7. So it's everything after or since the first exam. So it's Lewis Dot, it's the molecular structures, and then all of lecture 6, and then whatever we get through in lecture 7 today. So the video online was telling you, yeah,
You said lecture is what?
5, 6, 7. It was just telling you about that mole ratio. So what the meaning of a reaction is that the coefficients tell you how much of each thing reacts with each of the other things. And so one of these reacts with 5 of those to give 3 of those and 4 of those. These are our coefficients. You use those to make the mole ratio. These apply to both molecules. So one of these molecules reacts with 5 of these molecules to make 3 and 4. But they also apply to moles. A mole of this reacts with 5 moles of that to give 3 moles of that and 4 moles of that. And so they can be molecules or moles. So what we're going to deal with today is weight amounts. If you're doing a reaction, you have to know how much of each reactant you need. So you're going to figure, if I have 20 grams of this reactant, how much of this other reactant do I need to react with it? Or, more likely, you may say, I need 50 grams of this product. How much of each reactant do I need in order to give me 50 grams of the product that I need? That process of that calculation is called stoichiometry. And so, if you work it out, there are 4 types of stoichiometry problems. There's mole to mole, grams to mole to grams, and grams to grams. We're going to go through each one. We essentially have this flow chart here, and you can start at any of these places and go right. So you can go from grams of A to grams of B. That's the longest possible reaction. You can go from moles of A to moles of B. You can go from grams of A to moles of B, or you can go from here to here. You can start anywhere and stop anywhere, as long as you are moving to the right. So the simplest one is mole to mole. It's one step. This is just where you use that mole ratio. So over here, I have written sort of a cheat. This is not in the slides. Okay? So I would suggest writing it down and then deciding whether you want to use it. This is a dimensional analysis grid set up with units in there for you. In a couple places, there's already a number. So here is a 1 and a 1. And then in some other places, they tell you what number you need to put in. It's just dependent on the problem that you're dealing with. So we'll keep referring to this, okay? This is not on the cheat sheet, so if you want to use this going forward, you'll have to have it memorized. So the first type of problem we're going to do is a mole-to-mole conversion. So like with that flow chart, with this, we can start anywhere we need to start and stop wherever we need to stop. So for mole-to-mole conversion, we are going to go forgot my unit here. That's coefficient COEF, coefficient mole of A. So we're going to go from moles to moles. So we say A and B. A and B can be anything you want. Just A is the thing you're starting with, and B is the thing you're trying to calculate. A can be a reactant, and B is a product. You can go, they were both reactants, they can both be products. A can be a product, and B can be a reactant. That doesn't matter. It's just the problem is going to give you something that's known, that is A. The thing that you're trying to find, the unknown, is B. And so in a mole-to-mole conversion, we know the moles of something. So that is moles of A. The moles of B that we're trying to get is the unknown moles. So we use the mole ratio to figure out and do the conversion. The mole ratio is just the coefficient. So the mole ratio between that and that is 1 to 5. Oxygen to C3H8 is 5 to 1. That mole ratio is a conversion factor. It's a conversion factor that we can use as a step in dimensional analysis to figure out how many moles of B that we need. So in this case, we're going from moles of C3H8. We're going to figure out how many moles of oxygen we need to react with it. So 0.40 moles of C3H8 is what we're starting with. We obviously have at least one step. Let's come over here and look at our grid. We're starting with moles of A. So we're starting here. If we're starting here, this isn't a 1. This is the number that we're actually starting with. If you start in the first step, then that becomes a 1. But if you start here, it can be any number the problem says. So in this case, 0.4 goes here. If we're starting here, we never have anything directly underneath it, and so that and that get ignored. So we're going to go from here to here, and that says on the bottom is moles of A. Just like always, this gets copied down here. And the top is moles of B. What is our B in this problem?
Wait, why aren't we starting at the beginning again?
It's a stepwise thing. You can start and end anywhere you need to.
What is G?
Grams. So we'll talk about that when I think that's probably the next type of reaction we'll talk about. So in this case, we're only doing the middle part.
So if you have moles, then you start where the moles.
You start with the moles. If you have grams, you start here.
Okay.
So here we have moles, so we're going to start here. This says we have moles of A on the bottom, moles of B on the top. What is B here? We're trying to find oxygen. And so we put moles of oxygen. And then written up there, possibly legibly, it says COEF. I wrote that in there for coefficient. So all you have to do is look at the reaction and write the coefficient for each of these next to it. So what is the coefficient on oxygen in that reaction? 5. It's just the number in front of oxygen. So I put 5 there. What is the number in front of C3H8? 1. It's an implied 1, so I put a 1 there. Yeah,
We want to look at the left side because that's the problem. Well, not the left side, but the right side of the.
right. In this problem, we're going C3H8 to oxygen, and so we know in this problem we're not caring about the products,
Okay.
but this reaction question could say, if 0.40 moles of C3H8 reacts, how many moles of CO2 would you make? But it wouldn't really change anything we did, other than this would be CO2s, and that number would be 3 instead.
Okay.
So we've canceled that unit. In the top right corner, we have moles of O2, which is the unit we wanted. So we're done. So 0.4 times 5 is 2.0. So the answer to the problem is 2.0 moles of oxygen.
I don't really get how you know it's asking for moles of oxygen. It just says if.
That question is not written very well.
Okay, yeah, because it doesn't
No.
really give you any information.
I feel like some of that was kind of wrong.
Yeah. The wording was weird, like how
Is it?
they asked
Yeah.
about it.
It shouldn't. No.
A lot.
I think it was because I didn't know how to answer it.
Yeah, the Wiley asked a lot of.
Oh,
The
wow.
homework was very good.
I didn't even answer half the Wiley.
The majority of it was on the,
It was on this?
Yeah,
Okay.
like I got a 1 point something.
I'll have to look. If it was on this, I'll just, everybody will get full credit on it. I don't,
Number, I think, if I'm reading it right, it was number 6.
number 6,
Yeah. I don't have it here.
I'll take a look at it.
Okay.
But we'll get it. If it was literally this last week, you're not going to be held responsible for it.
Like I was just thinking, when you wrote that, that would have helped so much for this.
But I think what Wiley was molecules and atoms and grain and stuff like that. That's not this. That is not this. That stuff we went over.
Yeah, it was balancing the equation.
Balancing equations
Yeah.
we did.
Yeah,
Yeah.
that was on Wiley.
That was on Wiley. I know Wiley had grams, molecules, and atoms converting between those. That stuff we did though.
Yeah.
I don't remember this being on the homework.
Okay, I'll look. So here is another reaction. First question is, what is the mole ratio of oxygen to C6H6?
Um,
15.
15 O2s
To
to
two.
2.
So that's our coefficient, the coefficient that we're going to use as our mole ratio. The first problem is how many moles of oxygen are required to react with each mole of C6H6. This we can do up here, but this is more of a logic type question. This is just seeing if you understand what this means. So if we have one of these, how many of these do we need?
Say that again?
If we have one of these, how many of these do we need? If we have two of these, we need 15 of those. If we have one of these, how many of those do we need? Half of 15, which is 7.5.
Right, but we can't have 7.5 of anything.
You can't put a coefficient there, which is why it is 2 and 15, but you can have 7.5 moles of something.
Okay. All right.
And so the other way to do this mathematically is 1 mole C6H6, mole of C6H6. We're trying to get to moles of oxygen. These are our coefficients. The coefficient on oxygen is 15. Coefficient on C2H6 is 2. 15 divided by 2
7.5.
equals 7.5.
Okay.
So that's one that you can do in your head, but you don't have to. You can always do the math.
So that would be number 1.
That is, this is 2.
Oh.
That's 2.
So the ratio is 15?
Because it says oxygen to that, it would be 15 to 2.
That's what I meant, yeah.
Yeah. So number 3 is not something you can do in your head most likely. And so for number 3, we do have to do the math. But it's the same math. 0.38 moles of C6H6, moles of C6H6, moles of oxygen. Oxygen is 15. C6H6 is 2. And so it's 0.38 times 15 divided by 2. Somebody do that. Say it again?
2.85.
Thank you. So if you want to burn 0.38 moles of benzene, C6H6, it's going to suck up 2.85 moles of oxygen from the air. That's what that's saying. So here's another problem. The problem says, what is the mole ratio for determining the moles of CO2 that will be produced when 2.3 moles of oxygen react? So the first question is, what is the mole ratio?
5 to 1.
5 to 1. CO2 is, wait, 5, no. CO2 is 3.
Oh,
CO2 is 3. O2 is 5. So 3 to 5. Next question is, how many moles of CO2 will be produced? So what is the number that we are starting with in that problem? 2.3 moles of oxygen. That is what we're starting with. And so moles of oxygen have to come down here. What are we trying to get to in the end? Moles of CO2. So these numbers are just the coefficients. So what number goes with CO2? 3. And what number goes with oxygen? 5. 2.3 times 3 divided by 5.
1.4.
1.4? 1.4 moles of CO2. That's your answer. There's another one. You have a different reaction. It's given to us. Is how many moles of chlorine are required to prepare 0.62 moles of aluminum chloride. And so you know that you need 0.62 moles of aluminum chloride for some reason. And so you have to think backwards and figure out, if I want that much, how much of the reactants do I need? So in that problem, what is the number I am starting with? 0.62 moles of aluminum chloride. And what am I trying to get to? Moles of CO2. The moles of aluminum chloride automatically go down here. And I'm trying to get the moles of CO2. What number goes here? 3. The coefficient on CO2 is 3. Coefficient on aluminum chloride is 2. 0.62 times 3 divided by 2 equals 0.93 moles of chlorine. So that is moles to moles. Moles to moles are the easiest one. It's just one step. Now we're going to go grams to moles. So in this case, we're going to start in this box. But we're still going to end here. We're ending in the same place. We're just starting one step sooner. If we start here, that number is going to be a 1. There is nothing else you would put there. That number is going to be a 1, and that says MW for molecular weight. And so this number is going to be the molecular weight of whatever A is. And so this is basically set for you. That is given to you in the problem. And these are just the coefficients like we just did. So this is not that much more difficult. It's just a little bit longer. So we have our reaction. What it's asking is, we did the reaction, and we know we got 80 grams of oxygen out of the reaction. We want to work backwards to figure out how much of the KClO3 reacted to give us 80 grams of oxygen. So what number am I starting with? 80 grams of oxygen. So, looking at that over there, what is my unit here? Grams of oxygen. Oxygen in this case is my A. And so that says grams of A. And what unit goes up here? 1 mole of O2. So what is my number here?
It's the molecular weight.
Molecular weight, which is,
16.
careful,
Times
32.
Oh.
But it's O2, so there's 2 oxygens. Each oxygen is 16. We've got 32. Now, we still got to do the step that we just did in the previous slides. So we've got moles of oxygen. We're trying to get to moles of KClO3. So what number goes here? 2. That's the coefficient. What number goes here? 3. Done. You obviously have to do the math, but the math is the easy part. Setting it up is the difficult part. A lot of these, there's really no thought process that has to go in, other than what is my A, what is my B. And then everything else is just fill in the blank. That was given in the problem. That's always 1. That is just the molecular weight of that. And these are the coefficients. So there's not a whole lot of thinking involved here. So if you do this, I guess the answer's not there. Someone do this for me, please. 1.67 moles KClO3. Now, this type of problem is a whole lot more common in the lab. And that's what this is getting at here. It's because I can't look at a sample and say, that is 3 moles of oxygen. I can weigh it and get grams and go from there. But these numbers apply to moles and molecules. They do not apply to grams. So I can't just go take 80 grams times 2 divided by 3. That doesn't work. I have to convert my grams to moles, then I can use my coefficients. So that's what we did here. So another way to look at it, looking at the other way, it says 1.5 moles of KClO3 decomposes. How many grams of O2 will be produced? So this is a moles to grams conversion. So in this case, we're starting in this spot and finishing here. The first type we did went from here to here. That last one went from here to here. This one's going to go from here to here. So looking at that problem, what is the number we're starting with? 1.50 moles of KClO3. So based on what we have over there, what goes here? The coefficients. So moles KClO3. We're going to go there. We're trying to get to O2. And so this has to be moles of O2. O2 is our B. And this says we're trying to get to moles of B in this step. And this is just the coefficients. Oxygen is 3. KClO3 is 2. So now we go on to the next step. And this step is basically the same as what we did here. It's just upside down. That is always 1 mole. It is never anything else. On the bottom is going to be 1 mole, and that is just the molecular weight of B. So I have 1 mole of B here, and B is O2, and then I need grams of O2. What is the molecular weight of oxygen? O2? 32. It's set up. Just have to do the math. What does that come out to be? 72? Thank you. 72 grams of oxygen. So now, we've done 3 different types. We've done that one, here to here, here to here. The only thing that's left is here to here. But it involves steps that we've already used. It's just a matter of putting them all end to end. So this is a mass to mass problem. So this is sodium reacting with chlorine to give us sodium chloride. It says what mass of chlorine gas is required to react with 9.2 grams of sodium. So you want to make this in the lab. You go onto your shelf and you find out you have 9.2 grams of sodium. And you say, I want to react all of the sodium that I have. How much chlorine do I need to give it for it to react? And so you're going to measure your chlorine in grams, because there's no good way to measure it in moles. So you're going to measure it in grams. And so you're going to do this calculation. So what number are we starting with here? 9.2 grams of sodium. We are starting in the very top left corner of our grid over there. So when we started with grams, obviously grams of sodium comes down here. It's going to go up here. 1 mole sodium. Because we started on this step, that number is automatically a 1. It's only never not a 1 if that's where you're starting. So that's a 1. This is what? The molecular weight, which is 23, I believe.
Yeah, 22.99.
20. So we'll go 23. And then the next step, got moles of sodium. What do you want to put up here? Moles of chlorine. So chlorine is our B. Sodium was our A. What number goes here? 1. Yes, it's Cl2, but it's the coefficient, the big number in front of it. There's an implied 1 there.
Wait, why would chlorine go there?
Say it again?
Why would chlorine go there? Oh, the mass.
Yeah, we're trying to find the mass of chlorine.
Okay.
So what number goes here? 2. Coefficient on sodium is 2. So if you look over there, bottom right corner is 1 mole of B, always. So I'm going to put 1 mole of Cl2, and this is just the molecular weight of Cl2, which comes out to be 71. And so we have it set up. Does this come out to be? Oh, it looks like this one actually has. 14.2 grams of chlorine. So all of these problems are essentially the same problem. None of them are more difficult than any of the others. It's just some of them are longer. So it's figuring out where am I starting and where am I ending. If you can get this memorized, you can use that. But there's a fair amount of stuff there to memorize. What I have in my head is this. Grams of A to moles of A to moles of B to grams of B. So I have that flow memorized, but then I have to figure out, well, how do I get from here to here, and here to here, and here to here? Once you do it enough times, you remember anyways.
Was it testing like last time when we put your studies of questions
From Canvas.
from campus?
The A homeworks. Plus, I guess, lecture 5 was included on homework 5. And so the last few questions from the big homework,
That you just handed back.
the ones that I just handed back, I guess it starts with the Lewis dot stuff. That would also be what you need to study. If you have it.
Did you give that back to Everett?
I probably, it's possible you came in just before us. I have it up here. So it looks like question 35 and beyond from the big one, plus the 2 sets of Canvas homework.
How many questions are going to be on the test? Is it the same?
It's the same. So 20 multiple choice, I think, and then 3 written.
What if we don't have class on Thursday?
If we don't have class on Thursday, that won't impact the exam, but I'm planning on doing the same thing we did last time. If the college is open, I will be here, and you're welcome to join me. If it is open, I will make a call by noon on Thursday whether I'm going to offer an alternative or not. Okay? If it stays out in the ocean and it's sunny skies here, I'm not going to let you off the hook. But if it looks like it may possibly come here, I'll give an alternative. Because I know some people live probably right across the street. Other people live an hour away. Okay? The people an hour away I'm not going to make drive through bad conditions. So I'll make a judgment call by noon on Thursday. If the college is closed, obviously nobody has to be here. Everyone automatically gets full credit for that lab. But no matter what happens, everybody has to do the post lab. Okay? And so if I send out a reminder, something talking about the alternative, or the college gets canceled or closed, I will send a reminder saying you need to do that post lab.
And which lab is
I believe it's a mole.
Yeah.
That was the one we were supposed to do last, like that was last week.
We had the one that was the college department says to do last week is actually our makeup lab. So it's just a big naming packet. It's not really a lab. So I make it the makeup lab, and then I just use the lecture credit.
So what lab are we supposed to be on?
I believe it's a mole.
Okay.
Postal. Well, we don't have a post lab from last week,
No, 'cause we
and so there is no post lab due to 2 days from now. The post lab will be due from this week's lab, whether it happens or not, next Thursday. Say it again? Yes. Whether we have class or not. So, in the problems that we've been dealing with so far, there was one known number. But you can imagine a situation where you're in the lab and you say, I have 9.2 grams of sodium, I have 14.2 grams of chlorine. If I throw them together, how much product am I going to get? And unless these happen to magically balance out, you're not going to get the same answer from each one. So if you do the math with sodium, you figure out that you get 23.4 grams of sodium chloride. If you do another stoichiometry problem, starting with the 14.2 grams of chlorine, you figure out that you get 23.4 grams of sodium chloride. So in this case, they were magically equal to each other. So these are two completely independent stoichiometry problems, just like we did before. So we started with 9.2 grams of sodium, did all of that, and ended up with grams of sodium chloride. We got that number, and then we said, well, let me start with that. Ignore that, start with that. Do the same process, and figure out how much product you get. In this case, they give you the same amount, and so the answer is easy, 23.4 grams. In almost no cases will it come out balanced like that. What this is saying is conservation of mass. We'll talk about more of this in the lab. This is the basis of our lab this week. It says that when you do a reaction, mass is not gained, mass is not lost. So you cannot make matter, you can't make mass, and you can't destroy matter, so you can't destroy mass. And so the mass you start with has to be the mass you end with. And so if you start with that much and that much, when you put them together, you can just add the two together.
Okay.
In this case, in that case,
Yeah.
because they happen to balance out equally. So there's a question over here?
I think I'd like to do another example to get it, like what you're supposed to do if they don't have.
There will be.
Yeah, that's why.
Yeah.
That's why.
So this is a picture of what just happened there. We have 9.2 grams of sodium. We're putting it with 14.2 grams of chlorine, and we get 23.4 grams of our sodium chloride. So here is just another mass to mass. Okay? We only have one number to start with. This is not a balancing thing yet. So we're starting with 1.8 times 10 to the 8 grams of hydrogen. That's 180 million grams of hydrogen in a shuttle. We need to figure out how much oxygen is consumed when that hydrogen burns. So we're going to start with 1.8 times 10 to the 8 grams of hydrogen, which is H2. What goes down here? Grams of hydrogen. What goes up here? Moles of hydrogen. What number goes here? 1. What number goes here? 2. Essentially 2. Each hydrogen is basically 1, so we'll call it 2. What goes here? The coefficients. So this is moles of H2. We're trying to go to what? Oxygen. So this is moles of oxygen. Oxygen has a 1. Hydrogen has 2. This must be moles of oxygen. What unit goes up top? Grams of oxygen. What number goes here? 1. That's always a 1. And what number goes here? 32. So we've set it up. What does this come out to be? It's going to be a really big number, whatever it is. 7 0. Is there? Do you have a scientific notation?
It's like 1.44 times 10 to the 9.
Oh, I hate it.
1.44 times 10 to the 9th. That is grams of oxygen.
Okay, where did the 9 come from?
Brittany, can you put that in your calculator and then let me see what it gives you? Do you still have it?
Maybe I put it in wrong.
0.8 times 32. You've got 1.44. Move the decimal place over 9. So that is number 1. What mass of oxygen is consumed? Number 2 says what mass of water vapor is produced. So we're going to use basically 1.5 billion grams of oxygen. How many grams of water vapor are we going to make? So in this case, what number are we starting with? You can start with the same number again. 1.8 times 10 to the 8th. That's grams of hydrogen. This is all going to stay the same, but this is still hydrogen. 1 mole of hydrogen, 2 grams of hydrogen. This is where it changes. So this is 2 moles of hydrogen, but instead of oxygen, now we're going to water. So what goes here? 2 moles of H2O. And this is 1 mole H2O. What goes up here? 18 what? Grams of H2O. 18 grams of H2O. So this comes out to be 1.6 times 10 to the 9th grams of water. So you've seen, at least on TV, a shuttle taking off. What is always left behind the shuttle as it goes? It looks like smoke. So there's definitely smoke there. But what also does it look like? It's like a cloud, right? What's a cloud? Water. We just made over 1.5 billion grams of water. Which is why it looks like there's a giant cloud coming out from behind the space shuttle. Okay. So now we're going to get to a situation where things don't magically balance. Well, this is a good place for a break.
Yeah, don't erase that yet, please.
I'll leave that during the break.
grams come from?
That's the mass of water.
Oh.
Oxygen 16 plus 2 hydrogens. So we'll start at 7:30 on that clock, 12 minutes from now.
Can we take like a little extra time to go over the last section?
Yeah.
I'm gonna probably take longer than
Well, I'll take a look and see. I think we're not going to take very long to finish this, so we should have time. So go ahead and take your break.
Who am I concerned?
When are we starting? 7:30 on that clock.
Is the difference between
these, all of these equations from this.
He will. Explain to me why that's required.
How we can, how we can still kind of understand like the concept of like mass and mole and
The mass to mole is exactly what we're doing. That's the first step of stoichiometry is grams to mole. The last step is mole to grams. I think what really got most people is when you threw in Avogadro.
Yeah.
So,
And like when to use that, because why do you like, did you divide it by the, and I'm like, what?
Yeah, I feel like we didn't really go over that in class.
were there examples of that on the Canvas homework?
It was like, yeah, it was so many questions like that, I feel like, but we didn't really go over it. I had to go through the Wiley text and like find their examples to figure out how to do that problem. There's one
Looks like
question.
there's one here.
There was one question that I really had trouble with. I think it was
Like the balancing equations is fine because that's what we went over.
This one probably.
what is that?
How many moles of chloride ions are present in 18
Yeah,
point?
yeah, that's the one I missed. That's the only one I missed because I could not figure out how to do
So-
it.
That one and that other one were two that I missed.
We'll go through all these. We'll go through all.
About the lab, this is what I learned last week. It's a mole because it was after the last lab. we
Yes.
did. But
Yes,
so
that's what
we're
this week.
doing it this week.
Correct.
So we just like
Because
basically
we
skip.
basically have no lab.
Okay. Because then I printed homework actions and I was like, are we doing that this
You're
week?
just
I'm
saying
off
you're
by
just
one.
printing ahead a week. That's
I'm gonna stop doing that because it's confusing.
Okay.
I think you're right, I think this is gonna be the worst test.
it will be. have this. So, in the one reaction that we had given amounts of two different reactants. It happened to be that they were equal to each other. So they both gave the same amount of product. And so if you imagine the amounts of these reactants slowly going down as they react, they're both going to run out at the same exact time. That's normally not the case. Normally, you have more of one than you need, and so one of them runs out before the other one. The one that runs out first is what we call the limiting reactant. It's called the limiting reactant because it limits how much product you can make. When you run out of one of your reactants, you can't make any more product. And so the one that runs out is the limiting reactant. The one that is left over, we say, is in excess. Because we have an excess amount of it. We have more than we need. So this is an example. Here we have pieces of magnesium, and we're dropping them into acid. This is something we'll do in lab. But this is what it looks like when you do it. Okay, we have chunks of magnesium down here, and they're bubbling. As they bubble, the chunks of magnesium slowly dissolve and disappear. So that's what it looks like when it's happening. This is what it looks like when the reaction is finished. Looking at that picture, can you tell me which reactant, the magnesium or the acid, was in excess? The magnesium. How do you know the magnesium? It's still there. The acid is dissolved in water. And so that is going to look the same whether there's acid left over or not. So you can't tell by looking at the water whether there's acid left over. But it's clear that there's magnesium left over. If there's magnesium left over, it is in excess. So by default, the acid is the limiting reactant. If we let it go until it stops, and it looks like C here. Which one was in excess? The acid. The magnesium is gone. Because the magnesium is gone, it must have been limiting. If one of them is limiting, the other one is in excess. Remember, the limiting reactant is the one that completely disappears. Yes?
Are you basically just talking about which ones there's more of?
It's more complicated than that, though. Because if you have a reactant, sometimes you need 5 times as much of one as you need of that one. And so if you say, I have 7 grams of that one and 5 of that one, right? We'll see.
So the magnesium was the...
Magnesium was in excess in B. It was limiting in C.
Okay.
The leftover in B, so it's excess. It's gone in C, so it's limited. Remember, the limiting reactant is called the limiting reactant because it determines how much product you can make. So the problem you're going to see on an exam it's going to be, you have this much of this reactant, how much product can you make? And that's going to be determined by the limiting reactant. You're going to have to figure out which one that is. So here's another reaction. There's an iron nail in a copper solution. We let it react, and that's what it looks like at the end. Which one is the limiting reactant, the nail or the copper solution? How do you know it's the solution? What's dissolved?
Because the copper's still there.
The nail is still there. So we have two reactants, the nail and the copper. The one that is limiting will be gone. The one that's in excess will still be there. Clearly, the nail is still there. And if the nail is still there, the solution must have been limiting.
So to answer that question, we could just write CU.
You could either put CU, you could either put that, or probably more likely you would put that.
So when you said it, that limiting is the one that completely disappears, you didn't really mean that because it doesn't look like anything disappeared.
The blue here, turn to clear. This is a product. This is no longer a reactant.
Like rust is a product, right?
What the brown there is copper, not iron. I think an exam question would be more straightforward than that. And so we're going to do these problems. They're basically stoichiometry. But it all comes down to the fact that in order to make a product molecule, you need these parts to come together to make that. And it works the same as making this solar car. So to make a car, you need a frame, a solar cell, a motor, 4 wheels, and when you put them together, you get a car. So if you have these parts, how many cars can you make?
3.
Why?
Oh, wait. Well, you only have.
There's only 3 sets of wheels, so you're limited by the 3 sets of wheels.
Exactly. You're limited by the wheels. So yes, you can make 3. You can make 3 cars. The wheels are our limiting reactant. We have 4 frames, 5 solar cells, 6 motors. They're all in excess. What we're going to do is the same idea. You looked at that and immediately figured out, I'm limited by my wheels. Yes, if you're smart, maybe you can make a tricycle car and make more cars. But that's not an option. So here's a picture of a reaction. This is hydrogen reacting with oxygen to make water. This says that for every 2 hydrogens, you need 1 oxygen. So look at this picture. The white ones are the hydrogens. The red ones are the oxygens. Which one is the limiting reactant?
The oxygen.
How do you know?
Because there's less of them.
There's less of them to make the reaction.
There's less of them, but you need twice as many of the white ones as the red ones. And so you can't just go by there's more of the white ones.
There are more than twice.
There are more than twice. If you count, there are 3 red ones. 1, 2, 3, 4, 5, 6, 7, 8 white ones.
Right.
And so with 3 red ones, you need 6 white ones.
Right.
But you have 8.
Right, so you're in excess of 2, right?
Right. You have an excess of hydrogen, the white ones. And so the red ones are the limiting ones. So we're going to do these problems. They are stoichiometry problems. That's all they are. Okay, they're 2 separate stoichiometry problems, and then you compare the results at the end. Okay? There are 2 ways to do this. I'm only going to show you one way. It is the longer way, but it is the more straightforward way. The other way requires some logic. If I think this tells you how to do it, but I am not going to show you any examples in class. If you want me to personally show you an example, because you think you may want to do it this way, that's fine. I can do that. But I strongly suggest we do this way. One, it's more straightforward. It's the exact same type of stoichiometry problems we just did. And when you do this on an exam, there's almost always going to be a part B. And this way will also give you the answer to part B. If you do it this way, you'll then have to come back and do more problems to get the answer for B. So I am going to strongly suggest you only do it the way that we do it here. And that is to calculate the amount of product you get from each reactant and see which one gives you the most. So here's an example. This is our reaction. And it says here are three situations. We're starting with half a mole of P4 and 5 moles of O2. Which one is limited? So we are going to do stoichiometry. We're starting with moles of both. We can just go to moles of our product, because we just need to know which one gives us most. And then, so if it's the most moles, it's also going to be the most grams. And so we don't need to do that last step. We can just do moles to moles. So let's do part A. We're going to start with 0.50 moles of P4. We are going to go and figure out how many moles of product we can make. We've got moles of P4. We're going to go to moles of P2O5, our product. What number goes here? 2. This is the coefficient on P2O5. What number goes here? 1. So 0.5 times 2 equals 1 mole of P2O5. Now we completely ignore what we just did, and we start again with 5 moles of oxygen. Moles of oxygen goes on the bottom. Again, it's moles of P2O5, because we're trying to get to the same thing. This is still a 2. Oxygen is a 5. So we have 5 times 2 is 10, divided by 5 is 2 moles P2O5. To figure out which one is limiting, you figure out which one gave you the smallest amount of product. Which one gave us the smallest amount of product? P4. This one gave us 1 mole of product. This one gave us 2 moles of product. What I see people do is they do this, and they understand I need the smallest one. But what they then do is they circle that and write limiting. That is not the limiting reactant. That's not even a reactant. That's what you use to figure out which one was limiting. And that is the limiting reactant. You did all the hard work. Don't circle the wrong thing. Okay? Yes?
Is there a relationship between that chart and that chart? Or did you
What we just did, we did that mole to mole. The first one that we
Except mole wasn't 1.
Right, if you start here, that's not a 1. It's whatever number you're starting with. If you start here, that's a 1.
So is the answer just P4, do we have to put, like,
So P4 limiting?
P4 is the limiting reactant. However you want to tell me that, doesn't matter to me. Then we can do part B.
oh, okay. I thought we were supposed to choose like A, B, C.
Oh, no.
I was gonna ask like, well, so what's
No,
the?
that wouldn't make much sense. So, really the only thing that changes are these 2 numbers. And so, we can put 0.2 in there and 1 in there. Here we have 0.2 times 2 is 0.4. And this is 1 times 2 divided by 5 is 2/5, which is 0.4. So in this case, they're equal. You just tell me there is no limiting reactant. The last one, we have 0.25 and 0.75. 0.25 times 2 is 0.5. 0.75 times 2 is 1.5 divided by 5. What's 1.5 divided by 5? Three?
Is it 1.5 divided by 5?
Yes. Just 0.3?
0.3.
Thank you. So which one is my limiting reactant? O2. That one gave me the smallest amount. So that is my limiting reactant. Okay? So this would be part A on a multi-part problem. Part B would be how much product can you make? You already did the work. You just take the smallest one, in this case it's 0.3, and you write it for part B. So because it was the smallest one, that meant that was limiting, and that's also the amount of product you can make.
So that also means your answer for part B, like the 0.3 moles.
0.3 moles of P2O5.
Okay.
Sometimes part B will tell you that you need to do it in grams, so then you may have to convert that. And that's what we did. Here's another type of thing. We have different reaction, nitrogen reacting with hydrogen to give us ammonia. We have 2 moles of nitrogen and 5 moles of hydrogen. So we have 2.0 moles of nitrogen. We're just going to do moles to moles. And so moles of nitrogen, moles of ammonia. Figure out how much product you can make from each one. So this is just coefficient. N2 is a 1, ammonia is a 2. It's 4.0 moles of ammonia. And then we've got 5.0 moles of hydrogen. Hydrogen is a 3. So it's 5 times 2 is 10, divided by 3 is 3.33 moles of ammonia. So we did one step for each of them to figure out how many moles of ammonia we can make. So what is my limiting reactant? Hydrogen. It can only make 3.33. That one can make 4. That's a smaller number, so that's my limiting reactant. How many moles of ammonia can I make for that would be part B of the problem? 3.33 moles of ammonia. So that was A here. Now we can just switch the numbers, do part B. We've got 3.1 and 10.2. That's 6.2. Somebody do this one for me. .8. 6.8. What is my limiting reactant? N2. It gave me the smaller number. So how much product can I make? 6.2 moles of ammonia. So here, we were starting with moles. On an exam, you're more likely to have to do everything in grams. It's the same process though, it's going to be that whole thing, like we did, rather than this one step. So this is a great example of an exam problem. You have grams of each, figure out what the limiting reactant is, and then part B, how much product can you make? So we need to do two separate stoichiometry problems, one with 0.4 grams of aluminum, one with 0.6 grams of chlorine. Take that all the way to grams of aluminum chloride. So we're going to start with 0.4 grams of aluminum. Automatically, grams of aluminum comes down here. What goes up top here? 1 mole of aluminum. What number goes down here? It's the mass of aluminum, which is 27. Automatically, moles of aluminum come down here. What goes up here? First of all, what's the unit up top? Moles of AlCl3, the product that we're trying to go to. That's our B here. What numbers go here? The coefficients. So that's 2 and 2. Automatically, moles of AlCl3 goes there. What unit goes up top? What are we trying to get to?
Grams.
Grams of AlCl3. What number goes here on the bottom? A 1. 1 mole of that. And then, this up here. What is AlCl3?
About 133.
133? Thank you. 33 or 34?
Well, I got 133.5, so.
We'll do 4. So we've set it up, we do the math, and what do we do? I get 0.5. So, and anybody else got? Did anybody else get 0.5? Did you get something different?
Yeah, I got 1.98.
Now I got 1.98. 1.98 grams of aluminum chloride. So that's the first half. I did the aluminum, now I have to do the 0.6 grams of chlorine. Grams of chlorine, moles chlorine, this is always a 1. Cl2 is 71. Our coefficients, moles of chlorine comes down. we're going to moles of AlCl3. That's 2. Cl2 is a 3. And this last step is the same as it is up here. I got 0.75. Did you get the same number this time?
Yes.
Thank you. So, I figured out how much product I can make from each one. It's just what we did before with the moles. It's just, there were 3 steps instead of 1. But I ended up with amounts of product from each. So, my answer to part A, what is the limiting reactant? Cl2. Cl2 is my limiting reactant. It gave me the smallest amount, so that is my limiting reactant. Now B says, how much product can I make? What is my answer to part B? 0.75 grams of aluminum. So that's what I mean by, we already did the work for B. You might, if you can kill 2 birds with 1 stone, you might as well use this method for A. That way you don't have to do any extra work for B. This is as hard as a limiting reactant problem can be. There's no way you can be more difficult than that, because we did all of the steps. It can be easier, but it can't be harder. Yeah, Emily.
So basically the difference between the O we were given the mole number.
We were given the moles, so we were starting here instead of here.
Right.
And because we didn't have this part B, requiring us to go to grams of B here, we were able to stop at moles.
Right, so that was, okay. So we just made extra steps
We made extra steps.
by starting with grams.
Right. But when people write exams, they like to make extra steps. So if you can do this, you will get the matching question correct in any sort of exam you may see it.
But we have to memorize that.
If you want to have that memorized, you have to memorize it.
I mean, if you want to use it.
If you want to use it. If you want to use that, yes, you have to have it.
Right.
Basically, you have to.
Okay.
Back to the slide that was the mass to mass conversions, where it's like what mass of NaCl should be produced when in 9.20 grams in A reacts with 14.2 grams Cl2.
Mm-hmm.
Is that kind of like, because you said something about adding the two
So-
products together?
In that case, because they both give you the same number, then they both completely reacted. And so the entire mass of both reactants went into the product.
Okay.
You can't do that here because you're going to have a whole bunch of aluminum left over.
Yeah.
And so you can't just add these 2 together to get the mass of your product.
So you're gonna have to measure it for your recipe.
Correct. And so if you just added them together, what that would be the mass of your product plus the leftover aluminum. And that's not a useful number.
I'm just trying to, I didn't really get that slide. I don't know if I missed something you said, so that's why I was trying to figure it out.
Well, you won't have to do that conservation of mass thing as a number thing in lecture. We will use it in lab, but not really beyond that. So if you can do the math part of that slide, you're good.
Okay, so like what mass of NaCl should be produced? So
Correct.
if they were 2 different numbers, would you go with the smaller one?
You'd have to take them all the way to the end. You
Yeah.
can't just.
No, so you would like do both of these,
Correct.
and then what mass of NaCl should be produced? You pick
The smaller.
the smaller one. Okay, yeah.
It's like picking the number of tires or pair of tires.
Yeah.
Correct.
Those are just, okay.
The tires could give you 3 cars, the others could give you more, so you can make 3 cars.
Yeah, but we're limited, that's what's limiting.
Yes.
It just didn't, the way that it was phrased didn't ask what was the limiting. It just said what massive NaCl should be produced. So I just wanted to make sure that I was right and that you pick the smaller one if they're different.
Correct. So, if you look at these, the way they worked it out is slightly different. It'll give you the same answer. What they did is they stopped in this step here, got moles of AlCl in both cases, figured out which one was the limiting, and then converted that 1 to grams. In my mind, that is more confusing. It's a little bit less work, but it's a lot more confusing. So I left that slide in if you want to do it their way. But I strongly suggest take them both all the way to grams to begin with. And you don't have to worry about getting confused. Question? Okay. So the last thing we have to cover today is percent yield. It's easy. Okay? These problems, A will be what's the limiting reactant, B is how much product you can make, C is what is the percent yield. Percent yield is the amount, it's the ratio of the product that you actually made in the lab versus how much product you should have made based on your calculation. So if you make in the lab exactly how much you calculated, that would be 100%. What you get in the lab is what you call the actual yield. Yield meaning how much you made. What you calculated is the theoretical yield. On paper, this is how much you should make. And so when you put these numbers in, if you calculated grams, you can use grams. If you calculated moles, you can use moles. It doesn't matter. So this is your equation. It's just actual yield, how much you actually made, divided by how much you calculated you were supposed to make, times 100. So if you got in the lab exactly what you were supposed to, multiplied by 100 is 100%. If you were supposed to get 100 grams, and you actually got 50 grams, 50 divided by 100 times 100 is 50%. That's all that's saying. It's what percent of how much you were supposed to get did you get. It can be over 100%. If it's over 100%, that means something is wrong in your reaction. That does not mean there's something wrong in your calculation. Okay? When you run a reaction in the lab, it never, ever, ever, ever comes out to be 100%. Never. If it does, it's a fluke of nature. It just tells you how good did you do. And it's basically never going to be 100%. So this is an example. We're not going to do all the math, but this is a limiting reactant problem. We're starting with that many moles of chlorine, that many moles of sodium chloride. Oh, I guess it's simpler than this. We're starting with 0.2 moles of chlorine. That. It says we make, in the lab, 0.4 moles of sodium chloride. In the lab, we got 0.4. And so we had to calculate the theoretical. It's a one-step stoichiometry. Theoretically, we were supposed to get 0.4. So actual was 0.4, theoretical is 0.4. It's 100% yield. When you see this, you will have already done this calculation. And so let's say you calculate you made 0.75 grams of aluminum chloride. Part C would say something like, in the lab, you made 1.3 grams of aluminum chloride. What is your percent yield? And so you would go 0.75 divided by 1.3 times 100. We're going to stop there. We're going to not do that last one. Let's cross it out.
We don't need to do that.
Don't worry about it. It's more difficult than anything you would see on the exam. So let's take a look at this homework that was everyone's bane of existence over the week. So I'm guessing part A, the number one, was one of the easier questions.
Yeah.
And if it wasn't when you did it, hopefully now that we've done it a bunch of times today, grams to moles, now it is an easy question.
So we can use that for that.
Yes. If you want, it's just, we're going, in that case, we're just going from here to here.
Yeah.
So, this is the first time I've written that up. How many people plan to memorize that thing?
Like that?
That, yeah, that. Okay.
So we can't use that like atoms.
Atoms, yeah. So I guess if you had a problem, you had to go from moles to grams, start there and go there. So, number one, we got 193.873 grams of glucose, and it says the molecular weight is 180, so you don't have to calculate that. How do we get number of moles based on the number of grams? Yeah.
Glucose has a molecular weight of 180, so you divide 180 into.
Correct. So we've got 193.160.
It's 193.87. You can.
Oh, I took.
Yeah, you like combine.
And 1 mole glucose, and it says it's 180.160. Anybody remember what that comes out?
It's 1.07.
Oh yeah, that one. Comes out good that. Question 2 is one people started with, right? So, this is similar to this one. We just have to go add an extra step. So we're starting, we have 4.2 grams of carbon dioxide. Is there a way that we can go directly from grams